Okay, let's talk about Torricelli's problem and Heron's problem and solve it by incorporating calculus. I showed you in the very first lecture the solution by pure geometric means. That in the case of Torricelli's problem involved rotating the triangle by 60 degrees and doing something very clever. And in Heron's problem, in Heron's case, it was also something very clever and very beautiful, but required a great deal of geometric intuition. So with calculus, you are able to solve these problems quite easily without introducing a coordinate system. So let's start with Torricelli's problem. It's an unconstrained problem. Inside the triangle, we have to find a point from which the sum of distances to the three vertices is the smallest. And if you recall, the answer was it's the special point from which each one of these angles is 120 degrees. And that's called Torricelli's point. And here's the geometric proof. Let's recall gradient as a concept that does not require any coordinates. Pick an arbitrary origin and call this our function. The length of the segment that connects our variable point to a fixed point. So think about this as a function. So the value is small here, a little bit larger here, very large over here, far away from the origin. So this is one of the exercises in the textbook, and a problem for which it's very easy to determine the gradient by pure geometric considerations. So for example, which way does the gradient point? Which way would you go so that the length of the segment would increase the fastest? Which way would you go? Along. Yes, directly out. And how long, what is the rate of change? Well, it's clear. If you go 1 unit of length, the length of the segment will change by that same unit. So the rate of change equals 1. Remember, this discussion all depends on having the unit of length defined as part of the space we're working with. So the gradient will be the unit vector in this direction. So that's the gradient of the length of a segment. Points along the segment and has unit length. So now let's switch to this problem, where the function that we're trying to minimize is the sum of three lengths. It's the sum of this length plus this and plus the sum of this segment. So now we have to evaluate the gradient of this function, the function being the sum of the three lengths. And the point where the minimum occurs is the point where the gradient is 0. Now this statement would need to be justified, but that would be a different topic, a topic on optimization. But just for the purpose of this discussion, let's take it for granted that the point where the minimum occurs is the point where the gradient equals 0. But this is the gradient over a more complicated function. It's the function that's the sum of the three lengths. So the gradient will be the sum of the three gradients, right? The combined, that's kind of clear that the gradient of the sum is the sum of the gradients. I guess we've never formally justified it, but it seems quite reasonable. So to find the gradient of this combined function, we just have to draw the three gradients and add them all together. Well, here they come. Here's my unit, they're all unit length. So they're about all this long. Here's the gradient of this segment. Here's the gradient of this segment, of the length of this segment. And here's the gradient of the length of this segment. And the point, and we have to add the three gradients to find the combined gradient. And the point is the optimal point, or it is the candidate for the optimal point, where the combined gradient is 0. And in what sort of arrangements do these vectors need to be so that their combined sum is 0? There are 3 unit vectors. What's the only way to arrange 3 unit vectors? All you get to choose is directions. so that their sum is 0? They have to be at 120 degree length, at 120 degree angles. That's the only way to arrange 3 unit vectors in such a way that their sum is 0. So there we go. This point is characterized by the 3 angles being 120 degrees. And of course that implies that these 3 vectors, these 3 angles, are 120 degrees each also. How simple is that? Compared to the geometric proof, which was beautiful, I was kind of envious. I never found it, never probably would have found it, even if in the last lecture I claimed I would have, I probably wouldn't have. I bet it was beautiful, but very difficult to find. You really have to be a geometrically inclined person and highly trained in geometry to find something like that. It takes great ingenuity, whereas this, I see you guys are a little bit in a little bit of shock. Is that because of how easy it is, or you didn't quite follow this?
Isn't this also geometric?
Well, there's some calculus in it, because we talked about gradients. And we brought in, so for what we borrowed from calculus was the statement that the function attains the minimum at a point where the gradient vanishes. That's a statement from calculus. But it is geometric in the sense that there are no coordinate systems, no coordinates. So it's a beautiful mix of calculus and geometry. It is, in fact, so appealing that there is great temptation to just stick to arguments of this kind and never introduce coordinates. I would almost feel this way, that it's so nice and so intuitive and so visual and so effective, then why not try to avoid coordinates at all costs, because they come at a significant cost of loss of geometric insight. So I actually think a lot of people went down this path, and it's proven ineffective. That's just I've already talked about it in the first lecture, but I actually think that yes, this is beautiful and I like it, but to try to stick, no matter what, to avoiding coordinate systems is impractical. Now let's talk about Heron's problem. Heron's problem is having a straight river and 2 villages, A and B. A and B. And once again, finding a point where the sum of distances is the smallest, but there is a constraint. The constraint is that the point needs to be on the straight line. So we once again talk about the gradients, but we can no longer, in a situation where there are constraints, we can no longer state that the gradient has to be 0. When constraints are involved, the condition is that the gradient must be perpendicular to the constraint. Must be perpendicular to the constraint. I'll give you a quick intuitive reason why that is. So once again, assuming that, well, it's more visual when there are different distances. So assuming it's a point somewhere over here, where once again our function is the length of this segment and the length plus the length of this segment, and it's the combined function, so we're trying to figure out the combined gradient, and the combined gradient is the sum of the individual gradients. Here's the gradient of the length of this segment. Here is the gradient of the length of this segment. The gradient of the sum is the sum of these 2 gradients. And we need to find a point where the sum of these is orthogonal to the constraint. Here's a quick intuitive reason why that might be so. Because if the gradient somehow pointed in this direction, suppose this was somehow the gradient, then it's intuitively clear that moving a little bit to the left, if the gradient points slightly to the right, then moving the point to the right would increase the function, because it's kind of going along the gradient. Therefore, going to the left would probably reduce the function. So if the gradient is not orthogonal to the constraint, and we can move along the constraint and diminish the value of the function and therefore find a smaller point, a point where the function has a smaller value. So that's why the statement is the gradient needs to be orthogonal. So at the optimal point, the gradient is orthogonal to the constraint. So we're looking for a point, and maybe I more or less nailed it, where the
total gradient.
Where the combined gradient, the total gradient, is orthogonal to the constraint. Now, what point would that be at? If we have two unit segments, at what point would they combine in such a way that this would still be geometric, these are not coordinates, in such a way that their projections onto the line of the river cancel each other. And so that the only component that's left is the one orthogonal to the river. Well, it'll be exactly at the point where these two angles are the same. If these two angles are not the same, then the quote-unquote horizontal components won't cancel each other. The components parallel to the river won't cancel each other. And calculus calls for them to cancel. So it needs to be at a point where the two angles are equal. So once again, we've recovered our geometric insight with no geometric prowess whatsoever. Just look at the problem, apply calculus, the answer presents itself. So it's beautiful and, like I said before, quite enticing to try and stick to these methods, which proves in practical, and that's why tensor calculus comes in and rescues the situation by allowing you to work with coordinate systems, yet stick to objects that have geometric meaning. So that completes this segment. Let's actually stop it here just to make it easier to edit. Lengths corrected on the drawing. All right.